Good morning to everyone. Thank you all for being here. My name is Rafael Pérez-Estrada, and today I'm presenting the work Integrating Taxonomic and Functional Features for Gut Microbiome Health Indexing. First, I want to say that recent research have shown that gut microbes play a crucial role in human health. Specifically, they are closely related to nutrient extraction, metabolism, immunity, and even pathogenesis of certain diseases. So trying to measure the dysbiosis, which is a deviation of the normal microbiota community, could be a biomarker of human health. So currently, to try to measure these dysbiosis, we have certain indexes. For example, we have alpha diversity-based indexes. Also, we have the gut microbiome health index and health index based on a principal component analysis. But the problem with these first three indexes is that they are only based on taxonomic profile. More recent indexes, like the Q2 dysbiosis, also tries to integrate functional profile in order to improve these indexes. So our objective of this work is to enhance the health indexes using not only the taxonomic profile, but also the functional profile. So in order to do this, we received 613 taxonomic and functional gut profiles. Now, they were from two projects, the American Gut Project and the Human Microbiome Project. From these samples, we had 313 healthy samples and 300 unhealthy samples. Unhealthy meaning that they had either of these three diseases, which are ulcerative colitis, obesity, or Crohn's disease. Also, from these samples, we already have the pre-calculated taxonomic profiles and functional profiles, as well as some of the health indexes I previously mentioned. So what was our methodology? The methodology was to use the functional profiles to retrain the gut microbiome health index and the health index based on PCA. So as I said, we already had those pre-calculated indexes, so we could directly evaluate them using a balanced accuracy score. But what we wanted to do was to re-implement those indexes and retrain them using the new data we have with the taxonomy and also with the functional pathways. And after we retrain them, we would evaluate them with the same score, and then we could make comparisons between the models. So the performance evaluation was assessed using a strategy called the five-fold cross-validation. So what we did is that we have the data set, which could be either the pathways or the taxonomy, and we partitioned the data set into 5 parts, considering that each part has 50% of unhealthy samples and 50% of healthy samples on each partition. Then, after we partition the data set, we perform a cross-validation. So we take 4 of the 5 partitions to train the model, and the left-out partition is used to test the model. And we measure the performance using the balanced accuracy score. After that, we take another partition to test, and the previous partition now is on training. So we do this until we finish with all partitions, and at the end, we end up not with 1 evaluation, but with 5 evaluations. This makes the evaluation more robust and takes out the bias of selecting a particular partition. So first, we re-implemented the gut microbiome health index, and I'm going to talk about how it works just briefly. So basically, this index works as follows. We have some healthy related organisms and some unhealthy related organisms. From each group, we calculate something called the collective abundance, which we have the formula at the bottom of the slide. And basically, this index is the ratio of those collective abundances. And if that ratio is a positive number, then it's a healthy sample. And if it's a negative number, then it's considered an unhealthy sample. So what we did is that we took that same workflow, re-implemented, and we used the functional pathways also to train that index. So at the end, we ended up with three different types of that index, and an index based on the taxonomy, that same index trained with the functional profiles and the integrated pathways and the unintegrated pathways. So we ended up with three different indexes. So in order to integrate it all in a same index, what we did was an stacking ensemble approach in which all three indexes were fit into a random forest classifier. We trained them, and that classifier could tell us healthy or unhealthy. And well, the proposed method, which we call the RFGMHI, the previous method I mentioned, was the one to achieve the highest performance. This performance is the mean evaluation of the 5 evaluation I told you before. So it was the best resulting method. And as I told you, we also experimented with the principal components health index. So basically, this index works as follows. First, it performs a feature selection where it tries to identify the important, either the pathways or the important taxonomy. And then with just those features, it performs a data transformation, a scaling, and a standardization. And then it performs a principal component analysis. Then in the principal component analysis, it calculates three indexes, which are the hotel T-square index, the Q statistic, and the combined statistic. So with the reimplementation of this, we could see that the best performance of this model was not with the taxonomy, but with the pathways, with the functional profile, achieving almost a 78% of balance accuracy. And what we did next was the same as with the previous index. We tried to integrate all these three indexes in using the stacking ensemble approach. And finally, what we discovered was that both proposed methods, using this way of integrating taxonomic and functional profile, work better than the original models we had. There's a clear improvement in the methods. Finally, I want to say that we also conducted many additional analyses, but I don't have time to talk about them. But we also work with some other indexes like the MD index. We also built co-occurrence networks. And also we experimented with something called the topological data analysis. Specifically, we used a tool called TMAP, which is a mixture of the mapper and safe algorithm. And if you want to check the results of this analysis, you can check the GitHub repository. So finally, in conclusion, what we did? We adapted the existing indexes to work not only with the taxonomy, but with the functional profiles. And we developed a method of integrating all these indexes, and this way of integrating them outperformed the state-of-the-art indexes. Also, the results are on the GitHub. And just as a final remark, I want to say that we are currently working on a web tool to calculate all these indexes. The calculation of these indexes can be hard, and we really think that if we want to improve these indexes, continuous evaluation should be done. So as right now, we have like a beta version of what we call the gut microbiome health calculator, and you can just go in there, drag and drop your taxonomy or functional file, and the mentioned indexes are calculated. And finally, I just want to thank all the people that were involved in this work. This work was a teamwork from 3 Mexican universities, and I want to give credit to all these people that collaborate. Thank you.
Thank you, Rafael. So we have time for some questions. Well, Rafael, thanks very much. It's really interesting. So
training data set, you said there's HMP and another, and then we just contrast that with Alejandro's presentation about the global gut microbiome changes quite different in terms of if you've got African population, Latin American population, and North American. From what I can tell, a lot of your training data set is biased towards North American and European populations. Have you done any validations to see if there is how you can give it the Latin American or African population, how that microbiome health index performs?
No, actually, I haven't. It's kind of hard to get that data, but maybe with the Latin Biota data, I can do some evaluation. Yes, we totally should. Yeah, but I haven't yet.
Yeah, it was usually the same question. Andres, great talk. I was wondering, based, I understand trying to find out that the pathway-based method has better performance in terms of discrimination. So I was wondering if you have any supervised method in order to find out if there is a specific pathway that makes the difference. There are some pathways that you say that those are the ones that discriminate the most in the whole population.
Well, I haven't. Actually, when we did the model, we fitted the indexes, so we cannot. Well, when we use a supervised method, you can see like which are the features that are most important, right? But this classifier was trained using the indexes, like 3 numbers. So no, we haven't done that experiment, but we totally should.
Question? Yes. Do you have a question?
There's the microphone, so you can just.
Thank you, very nice talk. Maybe I thought I missed something of maybe you didn't make it, but when you were incorporating all the indexes, when you say the human integrated pathways, which are the databases integrated there, and what's the difference with the unintegrated one?
Okay, so let me go back a little bit. The thing is that the functional profiles that we had were the output from a tool called Human 3.0, and these give us 2 different outputs, the unintegrated pathways and the integrated pathways. So what we did, well, we separated them both just because we didn't want it to mix it, because the tool already gave us separated outputs, so that's what we did. But actually, what they mean is that like the level of specificity, the unintegrated pathways, as I understand, are like how can I say it? Like not recognized by the database, but we know that there is a pathway there. So it's maybe a very specific pathway from the sample, and the integrated pathways are the ones that we can really identify, like for example, pathways to biosynthesis of some compound, and etc.